Okay, I started recording already. So for today, I will teach you guys about the basic concepts of distributed force. Uh, I uploaded already the basic theory videos in the MS Team of our class and MS Team of the whole statics. Okay, so you can check there, the basic theory there. So please watch the video in sequence. The first one is supposed to be the distributed force. The second one is the how to find the internal force at one particular point. And the last one is how to find the internal force and the sorry, not the second one is not supposed to be finding the distributed force at one particular point, but finding the internal force and moment at one particular point. Then the third one is how to find the internal and moment diagram. Okay, so those three videos you're supposed to watch it. And actually, I forgot because I just uploaded today. Anyway, I will re-explain about the whole things about the distributed force. But before tomorrow's class, please watch the second video. The second video about the how to find the internal and internal force and moment at one particular point. Okay, at one particular point. So please watch the second video before tomorrow's class, because tomorrow I will explain about it. For today, I will concentrate on the distributed force. Okay, so up until now, the things that I explained to you guys was just related to concentrated force. Remember, right? Everything. Okay, everything was like this. Okay, correct, right? So up until now, everything that I have told you guys is about concentrated force. So so everything that I told you guys is about this kind of forces, concentrated force. So everything is just like happening at one particular point, the same as this one. So everything, we assume everything like this, concentrated at one particular points. Okay, but in reality, it's quite rare for us to have this kind of force concentrated at one particular point. Normally, when we have a force R, when it's given to one particular things, right, it happens on a certain area. So it will be distributed. So something like this. So whenever we have a ball like that, we put it on the floor like that. Okay, the simplified version is like this. R, the resultant force happening at one particular point. And at reality, this is why it's happening. It's distributed on certain area, the same as this one. Okay, the simplified version is like this. Okay, when we talk about two force member, okay, either it's under compression or under tension, we always assume that the force is happening at one point, but in reality, it's happening at certain area like this. So for these particular things, it happens here, like that. At this area, it's distributed like this. Okay, the same. When you talk about wheel, okay, we discuss it in some of the case that we discuss in the equilibrium, and you can see here, right? In the simplified version, we normally draw it like this, but in reality, this is what is happening, distributed at a certain area. So that is why it is very important for us to discuss about the effect of the distributed force in the structure. So you're supposed to know about it, because when we simplify things into a conservative force like that, and when we analyze it as distributed force, okay, the analysis is slightly different. Okay, the analysis is slightly different. So for example, if we have a beam, simple beam like this, okay, and if we put a force, center concentrated force in the middle like this, the effect will be different than if we put a distributed force like this. Okay, the effect will be different. That's why for today, we will concentrate on this. Okay, how can we handle this kind of problem? How to analyze the structure, how to analyze what is happening in the structure when distributed force is given to the particle structure. That's the thing that we will discuss today. Up until this point, anyone here want to ask a question? Anyone? No one?
Hello, sir.
Yes, yes.
So,
Who's this? Sik, okay. Sik
Ad-
or Ananda Azhar?
Azhar.
Azhar, okay. Yes,
Yes.
Azhar.
So, this is basically saying that uh, the apa ya, the distribution of the force will
Mm-hmm.
mengikuti will follow the shape of the, I mean, like that is circle, right? And
Oh, okay, wait.
there is C force like that, and it will be
Mm-hmm.
distributed to the shape of the circle, yeah. So it's
Uh,
distributed.
so this is the things in order to explain about the distributed force. But what you need to understand in this particular semester is not as complicated as this. It's not as complicated as this. Okay, for this one, there is a like a further study how can we simplify things, or how can we generalize things when we have things like this, right?
Yes.
What is really happening at the cross section? So there are further study about it, and for sure it will be distributed, but how the distribution goes, right? It depends on the cross section, and it depends on the area, and it depends on the location as well. But that's not part of our topics. But why I explained to you at the beginning is because that's the reality. Up until now, what you learn is just a simplified version.
Oh, I see.
So whenever we have things like this, the reality will be like this actually. Okay, but that's not the thing that we will discuss today and in this statics class, because for distributed force that we will discuss today is simpler than that. This one is more like an intermediate problem. So there is a further study for that. So the things that we will discuss, right, in the distributed force is more like this. When we have structure, and it's known from the beginning that we give the structure with a distributed force, what's the effect on that particular structure? So it's known from the beginning that the given load is distributed force, not concentrated force like this. Do you get it?
Yes.
Because the effect of the distributed force and conservative force is completely different. So like it or not, you have to know what's the effect of the distributed force given to a structure and how to handle that. Okay.
Okay, sir.
Any other question? Because it's for this particular things, right? Distributed force, internal force at one particular point, and internal force at the internal force and moment diagram, right? Those three topics is quite difficult. Okay, maybe it's the most difficult topics that you will learn in this particular statics class. I will try to teach you guys slowly, boy. So I will make sure that all of you guys catch up with the explanation that I give to you guys. Okay.
Okay, sir.
Any other question? If not, I will continue with the next one. Okay, no one? Okay then. So I will continue. So how can we calculate a distributed force? So for example, it's like this. This is like the generalized version of the distributed force. So when we have a distributed force, the shape of the distributed force can vary. Okay, it can be something like this. For example, just constant like that. The distributed force is constant like that. Or sometimes the distributed force can follow a certain equation like that. For example, it's like this, linear one like this. Okay, or even it can follow a more advanced equation like quadratic, logarithmic, or something like that. It can be anything. So this is another, okay, yeah, something like this, for example. Okay, but the question is not the shape of it, but whatever shape it is, okay, we have to find a certain way to handle it. Okay, the most important thing about distributed force is the total force. Okay, the resultant force. Okay, one thing that you must know when you handle a concentrated force like this, when you handle a concentrated force like this, okay, when you handle a concentrated force like this, okay, when it is a force, so it's supposed to be in Newton, like that. But distributed force, okay, because it's a distribution, okay, the units we use here is not Newton. Okay, we normally represent force as F, but for distributed force, we normally represent it as W. And W is actually a distributed force, and actually the unit is supposed to be force divided by length. So the unit is Newton per meter or Newton per millimeter or anything, yeah, any other units that you want, but it's supposed to be force divided by length. So in order for us to find the resultant force means the total force, which is caused by the distributed force. And the resultant force here is supposed to be in Newton. Okay, the resultant force here is supposed to be in Newton. Okay, so like it or not, when we have a distributed force, we have to multiply it. If we have a linear like this, in order to find the resultant force, we have to multiply it with the length of the distributed force. So basically, this particular area is actually the resultant force. W is representing the height, right? Okay, W is representing the height, and this particular length, and this one is the length. So if you multiply the height, which is the W, multiply by length, what you got, right? W is the Newton per meter. L here is the length in the meter, for example. Then you have force. Okay, so basically, the R, the resultant force, is supposed to be the area which is covered by the distributed force. Because W is representing the height, right? And this particular length here is L. So the area will represent the resultant force. And for linear like things like this, then you can use the equation for triangle. So this particular W multiplied by the length here divided by 2. It will be representing the resultant force. How about if we have an area like this, distributed force like this? Then we use integral. Yes, right. Then we can use integral.
But
Yep, Rizky.
So the W will be a function.
W, yes, W can be a function, but sometimes W, if W for this one, right? Okay, the W for this one, for this one, for the first one, the W for the first one, it will be a constant because it's a just constant, right? The value will be constant. For example, the W is equal to 7 Newton per meter. This is for the first case, this one. For this one, the W is supposed to follow a linear equation. For example, W equal to this one is this one 7x, for example. X is the distance from the this particular point. Okay, linear equation. For this one, maybe it's quadratic equation. W is equal to 25 multiplied by x squared, for example. It can be like that. The W will be in an equation, yes, but sometimes the equation is not given. For example, this particular things, right? If you have a linear distribution like that, sometimes the given value is just, okay, at this particular things, okay, the W is equal to 10 Newton per meter. Here, the W is equal to, this one is W2, W1 is equal to 0. Sometimes the equation is given, but sometimes not as well. It can be anything. Okay, it can be given. It may not be given as well. Yes.
So what if like the distribution of the force coincides with other external force?
Not necessarily. It can be. It may have a relation with that. It may not have a relation as well. So, but in order for you to calculate for the other external force, for example, at this particular one and this one, okay, yes, for sure, you have to consider it as a, you have to consider, for example, this and this, right? Normally, we have to calculate for the external force there, okay? You have to consider the distribution as well in order to calculate for the external force which is happening at here and at here. Do you get it?
But really, can you restate that again?
So basically, right, later I will give you some example on that. Because most of the time we have to find out the other external forces, which is happening at the joint, which is happening at the support due to the distributed force. So we have to consider the distributed force there. Okay, but before that, you have to know how to find out the resultant force, which is caused by the distributed force. So basically, when you have a distributed force like this, okay, the first thing that you're supposed to do is to find out the resultant force, because distributed force is just force per unit length. So you cannot calculate the force yet. So you have to calculate the force. Sorry, you don't have the force yet, the force value yet. You only have a force per unit length. So if you have a distributed force like this, the first thing that you're supposed to do is to find out the resultant force, the R. How to find out the R? Because as I told you from the beginning that the R, the resultant force in Newton, is supposed to be the area under the W graph, right? What you're supposed to do is just this, doing the integration. Okay, R is equal to integral of W dx. Okay, R is equal to integral of W dx. That's the first thing. Okay. What is R later? I will let you know what is R actually. And the other thing that you're supposed to know is the X bar. X bar is actually the location of the R. So basically, right, when you have a distributed force, for example, a constant distributed force like this, like the picture on the left, right? If you have a constant distributed force like that, or you have a linear distribution like this, distributed force like this, okay, you can represent it with the you can represent it with the R resultant force and the location of the resultant force. So basically, this kind of thing is equivalent, okay? This kind of thing is equivalent with this. R. This one, the one at the bottom, okay, is equivalent with this. R, like that. But the question right now is, what is the value of R? What is the value of the resultant force? That's the first thing. And the second one is the location of the resultant force. So these two values, R and X bar, actually are two values which can represent the distributed force. So basically, when you have a distributed force, you can represent it as a concentrated force at certain location. R is actually the representation of the concentrated force, which can represent the distributed force. Okay, X bar is actually the representation of the location of R, which both of these, okay, actually represent the whole distributed force. Do you get it, guys? Hello?
Oh, yes, sir.
Azhar, do you get it?
Yes, I do, sir.
So basically, it's like that. When we have a distributed force, we can represent it with a concentrated force. But the location, it depends, the location and the magnitude, everything depends on the distributed force itself. Okay, the first one is the resultant force, the concentrated force, which represent the distributed force, the R, okay, the resultant force is supposed to be the area under the graph. The area under this graph as well.
I'm sorry. You
Yep,
say
yep.
the area, sir.
Yeah, the area.
The R is the area, yeah.
Yeah, the area, the R is the area.
Okay.
That's why previously when the curve is arbitrary like that, you can use the integral because integral actually representing the area, right? R is equal to integral of W dx.
Yes,
So
area below the
yes,
curve.
correct. The area below the curve, the same as this one. Actually, we can represent this with the integral as well, but the results will be like this. Correct, right? The same as this one. If we do integral, the results will be like this. So actually, R is actually the area under the curve. The area under the curve. So the area under the curve of the distributed force is actually equal to the representative concentrated force, R. That's the first thing that you're supposed to know. Okay, that's the first thing. Then the second thing that you're supposed to know as well is the location where you're supposed to put R to represent the distributed force. Okay. The location cannot be just okay. Then I found the R. Okay, I can put it anywhere. No, it's not like that. You have to put it at certain location to represent the distributed force. How to find the X bar? X bar is actually the centroid of the area. Okay, if you have a square area, sorry, if you have a if you have a rectangle like this, okay, if you have a rectangle like that, right? The centroid is supposed to be there. Right? The centroid is supposed to be here. If you have an area of a triangle, then the centroid is supposed to be here. Right? So X bar is supposed to be representing the centroid. Okay, X bar is supposed to be representing the centroid. Okay, for a rectangle like this, the centroid is supposed to be exactly in the middle. So L per 2 from the left or L per 2 from the right. For triangle, okay, the centroid is supposed to be like this. 2L per 3 from the left, 2L per 3 from the zero point, or 1L per 3 from the maximum point. That's the location of the centroid, and that's where you're supposed to put your R, resultant force. So now, resultant force is actually the area under the curve. Okay, X bar is actually location of centroid. You get it, guys? Any question about this? Later today, I will give you some problem example as well, so you don't have to worry about it. So actually, this one and this one is actually they are the same, not the same, but I mean these things. This thing actually can represent this one. Okay, the same as this one. This thing actually can represent this one as well. So this one x bar here from the left is supposed to be L per 2. This one x bar here from the left is supposed to be 2L per 3. Like that. From this particular location, okay? This and this location are the same. This location and this location are the same. Here is supposed to be W multiplied by L. For this one, supposed to be W multiplied by L divided by 2 because of triangle, where W here is this particular length, the maximum. Okay. Any question here? No one? No one asking question for this? Yes, Rizky?
So if it's not triangle, neither rectangle, can we solve for one force like that?
Yes, the same. We can, but using integral like this. So this is the example of the things that you asked just now, right?
Yes.
That's key. So if the curve, the distributed force curve that we talked about just now is neither triangle or rectangle, okay, we can use integral, but the R is supposed to be same as the integral of W dx. X bar, okay, is supposed to be the location of the centroid of this particular curve. Okay, the location of the centroid of that particular curve. How to find a centroid of that particular curve? It's actually the same as finding a centroid of a certain area as well. How to find it? Then we can use this. So R is actually W dx, right? So R multiplied by X bar is actually the same as integral of xw dx. That's why X bar, we can find it by this one, xw dx, integral of xw dx divided by R, like this.
X bar is to find the
Location.
pengganti force-nya gitu kan ya?
No. R is actually the replacement of the force. Yes, R is the replacement of the distributed force. So
Jaraknya
R,
gitu ya, Pak.
R is actually concentrated force, which can represent the distributed force. But X bar is actually the location. Yes, the distance where we supposed to put the R. Do you get it?
Yes, sir.
So when we want to represent a certain distributed force, right? we have to represent it as a one concentrated force, which can represent the distributed force. But we have to put that one concentrated force at the correct location. Correct, Hazard?
Yes, sir.
Yeah, the correct location is represented by X bar here. X bar here. Okay.
But so what's the X inside the integral of X bar?
Sorry. What? What X here?
What does the X inside the integral represent?
Yeah. So basically, when we do integration, we have to define the dx first, right? So dx is any small length here. Okay, this is the dx, right? Any small length inside of the curve, right? And x is actually the distance of that particular small area from our origin. That's x. This one. This is x. This one is the x. X bar is actually the end results. Okay. I think it's quite difficult to explain it just by the showing the showing the equation like this. Later, I will give you an explanation using a problem example. I believe that one will be much easier for you guys. Okay, Rizky?
Okay, Pak.
And now, that's the first thing. This is when we have a triangle. It's quite common. Triangle is quite common. Then rectangle is quite common as well. Combination of both rectangle and triangle, rectangle and triangle is quite common as well. Okay, so if we have a combination of rectangle and triangle like this, what can you do? Okay, the easiest way is to divide the rectangle and triangle into two areas. Okay, so basically, if you see the whole things, right, it's actually a combination of rectangle and triangle. Okay, it's actually a combination of rectangle and triangle. Correct, right? Now,
Yes, sir.
one thing that we're supposed to do in order to handle this is, we know there is combination between rectangle and triangle, then we can divide it into two. The first one is the rectangle. Because rectangle, we know the R, we know the X bar as well. Triangle, same, we know the R. How can we get the R? And how can we get the X bar as well? That's why we divide it into two. For the first one, the centroid is there. The second one, the triangle, the centroid is here. So then later, we have a two. We have two resultant force. The first resultant force is actually representing the rectangle. Okay. The second resultant force is actually representing the triangle. And each of those R1 and R2 have their own location. R1 is actually if the left end is the origin, okay, R1 is actually L/2 from the origin. This one, L/2. R2, on the other hand, is actually 2L/3 from the origin because of triangle. So you can divide it like that. Okay, do you get it, guys? So whenever there is a combination between 2 or 3 shapes like that, then you can divide it based on its components like that. For example, this one, we have 2, shapes there, triangle and rectangle, then you can divide it into two, right? And we have two resultant force with two different locations for each of those. Any question here?
So if we
Mhm.
divided that by 2, can we
Mhm.
get one exact point?
Not necessary. You don't have to find one exact point.
So it's not necessary.
Yeah. So later, here, the representative of the structure, right? After you replace the distributed force with concentrated force, will be like this. One will be here, and the other one will be here. Okay, this one will be R1, which is equal to W1 multiplied by L. This one will be R2, which is equal to half of W2 minus W1 multiplied by L. Do you get it? Hello?
Yes, but
Good. So actually, that's the concept of resultant force. Sorry, that's the concept of the concentrated force. So the most important thing about not concentrated, distributed force. So the most important thing about when you have a distributed force, right? When you have a distributed force, the most important thing that you're supposed to do is to find out the resultant force R and the x bar, the location of the resultant force, which both supposed to represent the distributed force. Okay.
Sir,
Now, yeah. Who's this?
it's Jovan.
Yes, Jovan.
Can we combine the point of R1 and R2?
What do you mean by combine the point?
So we combine the force, so we only have 1 point.
Yes, you can. R1 and R2 then combine it into 1 point. Yes, you can. One resultant, right? Yes, you can. But what's the point of doing so?
For like moment or something?
Not necessarily. You can calculate moment one by one.
Shouldn't
You
it
get
be
it?
easier if we have 1 point only?
Sorry.
Shouldn't it be easier if we have 1 point only?
No, but in order to combine R1 and R2 into one concentrated force, right? You have to do a calculation as well. And later, so the amount of effort that you have to do to combine it will be the same as the amount of effort to calculate the moment one by one. So you don't have to do so. And most of the time, it will just complicate the problem. You get it?
Oh, yes, I get it, sir.
For these particular things, right? Because unless you are asked to do so.
Okay. Okay, thank you, sir.
Yep. Okay, as I told you before, right? For today, we will concentrate on this, how to handle distributed force. Okay, how to handle a distributed force. So the theory, the basic theory, I give all the basic theory. So for now, we will try to practice with several problems. Okay, we will try to practice with several problems. I think for this one, we will skip it because it will too long. It will be too long. So later, maybe you can use this as your homework. Okay, I will put it in the homework. But for this one, this is our first problem example. When we have a rectangle, distributed force, then this one, if we have a combination of a triangle and rectangle distributed force, and this one, when we have a certain distribution which is not triangle or rectangle. Okay. So those three exercises, I think we will try to do it today. Okay, now the first thing, try to understand the problem first. Okay, I will give you 2 minutes to understand the problem. Okay, so I will give you 2 minutes to understand the problem. Then after this, we will discuss about the solution. Okay, 2 minutes from now. Okay, I think it's not supposed to be that hard, right?
See what?
So basically what you're supposed to find is just the reaction force at A and at B. Okay, because just now risky, right? Because just now risky said that it's easy. Please help me to do this, risky. What is the value of the resultant force?
So it's only 300 millimeter
300 millimeters
times by
6 kilonewton per meter.
times by 6.
Yeah, but you cannot use 306 because this one is in meter and this one is in millimeter. Which one do you want to use?
Yeah, I didn't see that. Sorry. I think it's
1.8 kilonewton.
Yeah, so it's supposed to be
Yeah.
0.3, right? 0.3 meters multiplied by 6 kilonewton
6
per meter.
So it's 1.8 kilonewton.
Yes, yeah, 1.8 kilonewton. So that's the resultant force. Now,
Yeah, and
the location,
because it's a rectangle, just divided by 2.
so it's supposed to be exactly in the middle, right?
Yes.
So it's supposed to be
150
exactly in the
millimeter.
middle. Yeah, so the centroid is supposed to be exactly in the middle there. It's supposed to be 50 millimeter from the left, right?
Yes.
So X is supposed to be, if this is our origin, okay? So X there is supposed to be 150 millimeter, right?
Yes, 150 millimeter.
Now, the next thing is we have to find for A and B, resultant force at A and B. So it's not yet finished.
Yes.
The second things, the things that we have to do after that is what?
We know that in A is a pin, so there will be an AX and AY.
And B?
And B, because it's a roller, it's only BY.
Then after that,
we can just use a moment at A or a moment at B.
No. You skip one thing. You're supposed to draw the new free body diagram.
Yeah,
Okay.
sorry.
Yeah, you're supposed to draw the new free body diagram. So the new free body diagram is supposed to be like this. Okay. At A, just now you said that it's supposed to be just A. There will be AY and AX, right?
AX and B only BY.
UI. Then what are the external force that we have?
150 millimeter from the A point. There will be a force coming down, 1.8 kilonewton.
Yes, correct. 1.8 kilonewton. With the X here is 150
millimeter.
Yeah. So this is it. This is the free body diagram that you can solve. So as I told you, the importance of finding X bar and R value is to by doing so, then you can handle the distributed force as a conservative force at certain location. In that case, then you can, in that case, then you can calculate for all other external forces. Okay, in this case, then we can calculate for other external forces. Which one that you want to find first, Rizky?
By is using moment at A, because
Okay.
there is two force at A.
Sigma moment at A equal to 0. Then what you have there is
1.8 kilonewton times by 150 millimeter.
1.8 kilonewton
times by
times
150 millimeter.
150 millimeter. What else?
And with clockwise, so minus By.
Minus By multiplied by
times 600 millimeter.
600 millimeter equal to 0, right?
Yes.
Okay. Then what you have here?
So we got the By. Wait. 170 divided by 600. 0.45 kilonewton for By.
Yeah, 1.8 kilonewton multiplied by 150 millimeter divided by 600 millimeter. So basically it's divided by 4. So By is 0.45, right?
0.4, yes,
Yeah.
0.45
kilonewton. This is By. Then the last one is using sigma Fy equal to 0. What you have here is what? I'm asking you, Rizky.
0.45.
Okay, 0.45.
Yeah, 0.45 kilonewton.
Kilonewton
plus Ay equal to 0.
Plus Ay, so yeah.
Ay equal to 0.
No.
Ay is
not this one.
minus
Minus
1.8.
1.8 kilonewton
1.8
equal to 0. Then here Ay is supposed to be, what is that?
1.8 kilonewton minus 0.45.
Yeah, so this one, right?
Yes.
Yes. Y. Then the last one is using sigma Fx equal to 0. What you will have is Ax equal to 0. So this is what all of the external force that you have. Okay, Rizky, that's simple, right?
Yes, Pak, very simple.
So that's the way to handle a distributed force. When you have a distributed force, the first thing that you're supposed to do is to find out the R, resultant force. The second thing that you're supposed to do is to find out the location X bar. Then after that, you handle it as a concentrated force at certain location, X bar location. Then find out the other external forces. That's the thing that you're supposed to do in order to find out, in order to handle the distributed force. Okay, how to handle distributed force in order to find out other external forces. Okay, only to find out the external forces. So this, all of this simplification, okay, all of this simplification will work well. So representing the external, representing the distributed force with R and X bar, concentrated force at certain location, will work well in order to find out the external forces, like this, Ay, Ax, By. Okay, if you are asked to find out the external forces due to distributed force like this, then you can represent the distributed force as concentrated force at certain location. Yes. But later, there is a limitation on that. Sometimes you cannot do this. Okay, you can only do this only to find out the external forces. You can do this in order to find out the external forces. Okay, so if the question, the other question like this is to find out the reaction at A and at C, then you can do the same way as before. Okay, represent the distributed force as a concentrated force at certain location. This one is actually quite simple, right? Actually, this one is actually consists of one rectangle and one triangle. So, this one is actually consists of one rectangle and one triangle. So this one is the rectangle. And this one is the triangle. So it's quite simple. Each of those, you have to represent each of those with one concentrated force. Okay, then I will just discuss it, but I will not answer it until the end. Okay. So for this one, there will be one concentrated force in the middle here, which represent the rectangle. Then there will be a one concentrated force here, which represent the triangle. Okay. Rizky, please please point out one of your friends to help me to do this. Hello, Rizky.
Yes, Pak.
Yeah, just
I will point. Anyone?
Anyone that you want.
Okay, I think it's Matthew.
Matthew. Nah. This is Matthew.
Why, Pak? Because it's too smart.
Don't ask Matthew, the other.
Okay, I'll ask. Wait, let me look real fast. Samuel.
Okay, Samuel. Hey, Samuel, please help me to do this, Samuel. I explained to you, right? So this one is a combination of a rectangle and triangle, right?
Yes, sir.
So I don't want you to solve for A and C, but what I want you to do is to help me to complete this particular free body diagram.
Okay, sir. So where do you want me to start? From the distributed force or the
distributed force? So R1 and R2. So try to find the value of R1 and R2 and X1 bar and X2 bar.
So for R1, I think you just multiply 15 with 4.
Okay, 15 kilonewton multiplied by 4. So it's 30 kilonewton.
Yes.
Then R2?
R2 is a triangle, so 1/2 times by 15 times by 2.
Okay. 15, 2. So it's 15.
Yes.
Okay, 15 multiplied by 4 is not 30, right? Oh, how stupid that?
60, sir, 60.
Yeah, it's supposed to be 60. That's my mistake. Okay, 60 kilonewton and 50 kilonewton. That's R1 and R2. How about X1 bar and X2 bar?
Since it's a rectangle, we can use the midpoint of the rectangle. So it's 2 meters.
2 meters. So if our origin is from the left, right?
Yes.
X1 bar is supposed to be 2 meters. How about X2 bar?
X2 bar, it's a triangle, so we can use 2/3 multiplied by the length.
Yeah, 2/3 multiplied by the length. But remember, if you use 2/3, it's from this particular point, right?
Oh, right, sir.
If you want to use this particular point as your reference, then it's 1/3. Okay?
Yes.
So which one do you want to use? 1/3 or 2/3?
1/3, sir.
1/3 is better. Yes. Okay. 1/3 multiplied by 2 meters. So it's supposed to be 2/3 meters
plus 4.
Plus 4, correct. So 4 meters plus 1/3 multiplied by 2 meters.
Yes.
Okay, so it's supposed to be 4.6667 meters, like that. Yeah, 66666 meters, correct, right?
Yes, sir.
Okay, so we have our x1 bar and we have our x1, x2, x1 bar, x2 bar, r1, r2. We have those, all of those. And then beside that, we have, okay. The other thing that you're supposed to find is this value.
Yes.
What is the tension there?
Half of the weight of the
weight. So if we draw the free body diagram of this particular pulley, supposed to megagram. Megagram is supposed to be okay. This one is quite odd, you know, using megagram there.
I never seen that before.
Megagram, they're supposed to just use 2 tons like that. Okay, it's 2,000 kilogram.
Okay, sir.
So, or you can we just use 20. Sorry, we just use 20 kilonewton directly, multiply by 10. Okay,
yes,
so
sir.
20 kilonewton. Then we have tension force here, T1, T2. What is the value of T1, T2?
It's 10 kilonewton each.
Okay, it's supposed to be 10 kilonewton. So here is supposed to be 10 kilonewton. Here is supposed to be 10. Here is supposed to be 10 as well, right? Okay. You're supposed to do the calculation correctly, but I will not do it here for this particular things because it's part of the equilibrium. So you're supposed to be able to do it directly about that. Okay, yes. Then here at point A and at point C, what is happening there?
There are reaction force, sir.
At A?
At A, there's 2 reaction force, AY and AX. While at C, there's
X. At C, there is
only
CY.
Y, yes, sir.
What else? That's all, right? And beside that, we have to put all the reaction force, our reaction force. So here we have R1, which is 60 kilonewton. Correct, right?
Correct, sir.
Then here we have R2. R2 is the value is 15 kilonewton.
Yes.
Okay. The distance here is 2 meters. The distance here is supposed to be 2 meters. Sorry.
2.667.
Yeah, 2.666 meters. B, then there is a tension force at B. The tension force value is supposed to be 10 kilonewton.
Yes.
Then CY. That's all. Supposed to be like this, right?
Yes, sir.
Okay, thank you very much. So after you find out this particular free body diagram, then you can solve for AY, AX, and CY. That's simple.
Yes.
Okay, thank you very much. For all of you guys, as I told you, whenever you have a distributed force, you can convert it into a concentrated force at certain location, okay, by finding R value, the resultant force R value, and the X bar, okay. But remember, that kind of way can only work to find out for the external force, like this. So as long as the one in question is external force, then you can do like what I teach you guys. Okay, you can do like what I teach you guys, as long as the one in question is external force. Okay, so for this one, then you can use three unknowns equations, three unknowns, three equation. Then you can solve for sigma fx, sigma fy, and sigma moment. That's all. To find out for ax, ay, and cy. I just know who helps me to answer the previous question.
Me, sir, Samuel.
Samuel, okay, Samuel, please point out another one here to help me to do so, to help me to finish this particular problem.
Zik, sir, Zik.
Zik is, I know, please try to point out somebody else who rarely ask question in the class.
Rarely ask question. Nuki, sir.
Nuki? Okay then, Nuki.
Yes, sir.
Nuki, based on Samuel information, you rarely ask question in the class. Is it correct?
It's not rare, but sometimes after I want to ask something, people already asked it before. So
okay, yeah.
And my way of learning is watching and rewatch. I understand when after that I do.
Okay.
Usually.
Actually, I was just kidding because I thought you are one of the active students in the class. So, but anyway, help me to do this.
Sir. So we need to determine the R first.
But what do you think about the shape?
The shape.
Is it it can is it a combination of two shapes or just one shape? One shape without combination. This one.
I think it's combination of two shapes, sir.
It's correct. It's triangle and rectangular, right?
Yes.
Okay. So actually, the first thing that you're supposed to do is to divide it. Correct, right, Nuki?
Yes, sir.
Yeah, like what I told you before. So divide it into two. With the first one, sorry, because I throw it in my laptop, so the line is not straight like that. So the first one is rectangular, the bottom one. The second one is triangle, the top one.
Yes.
Okay, if I represent the first, because we're first representing the rectangular is R1 and triangle is R2.
R2.
Yeah. Then please help me to find out the value of R1 and R2.
Okay, sir. So the R1 should be using 6. 6 is for triangle, 2 for the rectangular, sir.
Yeah, so this one, right?
Yes.
6 is this particular length.
Yes.
The length from here to the length from here to here is 6. 2 is the length from here to here.
Yes, so in rectangular, using 2, right, sir?
Yeah, correct. 2 multiplied by?
2 multiplied by 7.
Okay, 7 meters. And so what is the value?
14, sorry.
We have 14 kilonewton. Okay, so that is R1. Then how about R2?
R2, we are using 4.
Why 4? Why 4?
Well, we already used 2 on the rectangular, so
yeah. So this one, right?
To use 4. Yes.
Yeah. The height there, the height of the triangle there. So it's supposed to be 4 kilonewton per meter. Okay, so 4 kilonewton per meter.
4 kilonewton per meter times 7 and time a half.
Times 7.
And time a half.
So
we got 14.
14 as well. Okay, now, x1 bar.
Yes, sir.
What is the location there?
It should be on the middle, so it's 7 divided by 2 on 3.5 meter.
3.5 meters. Okay, so around here. Okay, 3.5. But remember, 3.5 here is from the left side or the right side, right? It's not from the end here, but it's from this particular one. So 3.5 is actually from, if we have to make a line, it's like this, right?
Yes, sir.
3.5 meters, x1 bar. Now 3x2 bar.
The x2 bar is for the triangle, so it should be half. I'm sorry. 1/3.
1/3
times by 7.
Okay, 1/3 times by 7 meters. 7/3. Okay.
It should be 2.1.
Right?
Yeah.
Okay. But it's from the left or the right side?
It's from the right side, sir.
No.
I'm sorry, left side, sir.
Yeah, correct.
Left side.
Left side. So 1/3 is supposed to be from the long one, the tallest one. Okay, from the 0 point, it's supposed to be 2/3. Okay.
Yes, sir.
Don't mix up both.
Yes, sir.
So this is it. Yeah. So roughly here. That's the location, 2/3. Okay. So this one is supposed to be 2/3 from this to this to 1/3 meters. Okay, now?
Yes, sir. Now we draw the free body diagram.
Right. Drawing the free body diagram.
Which on A point we have that is fixed point, sir.
That's
so
fixed.
It should be only AX, I guess.
No. Fixed is not just AX.
AX
this
and AY.
AX
and AY.
AY. Okay, fixed. There is one additional things. When you have a fixed boundary condition like that, you will have like this.
Moment A. Okay, sir.
Yep. So basically, fixed is like when you climb it up, when you climb one of the side, when you climb one of the sides, right? This side it can handle X forces and Y forces, right? It can handle moment as well. So it can handle moment as well. That's why we have moment A, reaction moment A here, AX, AY there. Okay.
Okay, sir.
So whenever you have a fix like this, always have 3 external force there, because it can give 3 external force like that. Okay. Then the next thing that you're supposed to draw is what?
We draw our external forces, the R1, R2, and the 12 kilonewton.
Okay. R1 from the left edge from this one, what is the distance?
From that, it should be 5.5 meter.
5.5 meters, right? 5.5 meters around here. This one is supposed to be R1, where R1 is 14 kilonewtons, right? So you're supposed to draw it as 14 kilonewtons. 14 kilonewton.
And the R2,
5.5 meters. Then R2?
2 plus 2
1/3
times.
Okay.
Hold on, sir. Let me calculate it. So
yeah,
I'm kind of
4.3333, right? Of course. That's simple, right?
Yes, sir.
Don't confuse yourself.
Yes.
Okay, so it's another 14 kilonewton. And the distance here is 4.3333 meters. What else there?
And 12 kilonewton, 7 meter from the left.
Okay, 12 kilonewton here. Okay, now how many unknowns and how many equations?
We have 3 equations and 3 unknown.
We have 3 equations. Sigma moment equal to 0, sigma Fy, sigma Fy equal to 0, and sigma Fx equal to 0. And we have 3 unknowns as well, right? MA, AX, and AY. Can we solve for this?
We can, sir.
Okay. Please solve it now.
So first we use the moment, I guess, sir.
Moment at which one?
Moment
at
A.
Okay, sigma moment at A. Sigma moment at A equal to 0. What we have there?
We will have Fy. Ay, I mean.
Ay? No. Fa, Ay, and Ax will not have any effect. Right?
We have, yes, it's fixed position, so it will not move. I'm sorry, sir.
Yeah.
We have 12 kilonewton
multiplied by
7.
Then what else?
And then 14 kilonewton multiplied by 5.5.
14, 5.5. Then?
And then plus the 14 kilonewton times by 4.333 meter.
And then?
The moment at A.
Yes, correct.
We are finding, right?
You're supposed to put it there because moment at A will not be gone if you put the sigma moment at A. Sigma moment A there, it will be there for all the points in the beam. Okay, equal to 0 then. Then in this case, we have moment A equal to?
Answer, I'm calculating. It should be 221.2 negative.
221.2 kilonewton. Nah, moment. When moment you cannot just put kilonewton there. Kilonewton meter. Okay.
Yes, sir.
Don't forget about the unit. Okay, kilonewton meter.
Yes.
Minus means my
we
direction
have
there
the wrong
is,
direction.
Yeah. So in this case, it's supposed to be counterclockwise. It's supposed to be counterclockwise. So that's why it's supposed to be 221.2 kilonewton counterclockwise. CCW. Okay, moment A is okay now.
Now at X first, sir.
Now X the
sigma
easiest
fx
one.
equal to 0, Ax equal to 0.
Yeah, sigma fx equal to 0, then Ax equal to
0. And now the sigma Fy equal to 0, sir.
And
we
sigma Fy equal to 0.
Yes, Ay minus 14 minus 14 minus 12.
Ay
minus 14 minus 14 minus 12.
Equal
so
to 0.
It should be 14 kilonewton.
Yeah, correct. 40 kilonewton. So that's Ay. So this is it. Ay is 40 kilonewton. Moment at A is 221.2 kilonewton meter here. Kilonewton meter counterclockwise.
Sir.
Okay.
Yes, sir.
So it seems like you understand, right, Nuki?
Yes, quite. I think. I don't know, sir.
Well, you don't know. You're supposed to understand.
Sometimes I feel that I already understand, and then when I try to solve the same problem again, I kind of forget. So I might need to watch it again.
Yeah,
from YouTube.
Just keep practicing. Okay.
Yes, sir.
Okay, good then. Okay, Nuki, sorry, not yet. Please help me to point out another person.
Maybe
for this one is the person who you think that is smarter than you.
Well, there will be a lot, sir. So maybe Fahri and Aswin, sir.
Fahri. Huh? Sorry?
Yes, sir.
Fahri, you mean?
Yes.
Fahri. Okay, Fahri, please help me to do this, Fahri.
Yes, sir.
Okay, Fahri. Now this is the hardest question for today, Fahri. So you got the you got the bragging rights to solve this particular problem. Okay.
Okay, sir.
The question is the same as before, as this one, as the previous one that Nuki solved, is to find out the reaction force at point A. But this one, the the force, the distributed force, which is given there, is actually not linear, not constant. So it has a certain equation like that. It follows certain equation like that. W is equal to kx to the power of 1.5. Okay. The things that I want you to do is to help me to find out the value of R and the value of X bar. That's all. So basically the same as before, right? The reaction force that we're supposed to have at point A is supposed to be AY, AX, and moment at A, correct, right, Fahri?
Yes, sir.
It's the same like this. But the most difficult one is to find out where is the location of R and what is the value of R. So the value of R here and the location of it, X bar here. Your job is just to find out the value of R and X bar here. Hello, Fahri?
Yes, sir. Okay, sir.
Can you help me to find it out?
I think we use integral.
Okay, but remember, this equation is not yet complete, Fahri.
Oh, we should find the k, yeah?
That's correct. How to find the k? Remember, right? This the graph here, the curve here is supposed to follow this particular equation, right? So it's x to the power of 1.5. The problem there is the k, the value of k there is not yet known, right? Only that value of k there is not yet known. So the first thing that you're supposed to do is to find out the value of k there based on this value and this value that you already know. Correct, right? At x equal to 0, okay, the w is equal to
0.
Remember, right? The w, the origin of the w is from the left side. So x equal to 0 is this particular point, and at this particular point is x equal to 5 meters, right? So at x equal to 0, the w is equal to 0. At x equal to 5 meters, what is the value of the w?
4.8 kilonewton per meter.
4.8 kilonewton per meters. Then use these two values to find out for k. Can you do that? Yes, it's actually very simple, right? If we use the x equal to 0 and w equal to 0, later we put x equal to 0 here and w equal to 0 there, it will be 0 equal to 0. Yes, it's correct, but it's not solving the k, right?
Yes.
And use the other way. Use the other one. 5 meters. Okay, w is equal to 4.8 kilonewton per meter. Okay, when x equal to 5, right?
Yes.
So I can put it this way, right?
Yes, sir.
Okay, what I do is just putting this value here and this value here, correct, right?
Yes, sir.
Can you find out for k here?
0.429, 0.43, I think.
No. Don't use that. 0.
Yeah, 0.43.
0.43. Okay, that's k is 0.43. Then our equation becomes w equal to
0.43 x to the power 1.5.
Correct. 0.43 x 1.5. Now you got the w. How can we find the r?
use integral.
Okay, we can use integral. Okay, we can use integral then. So R is actually what? Integral of
0.43 x to the power.
Okay. R is supposed to be W dx, right? From x x0 to x1. So in this case is integral from 0 to 5, right?
Yes.
Okay. W is actually 0.43 x to the power of 1.5 dx, like this. Right?
Yes.
Can you help me to find out the value?
Wait, so.
X to the power of 1.5, integral of that is what?
One over 2.5 x to the power 2.5.
Okay, so it's supposed to be 0.43, 2.5 like this,
Yes.
x to the power of 2.5 like this, right?
Yes.
Okay, and the limit is from 0 to 5.
0 to 5.
What is the value there?
With 62, sir.
Sorry?
9.62.
Who's this? Matthew, right?
Yes, sir.
9.6. 9.62 kilonewton.
Yes.
Okay. Then how can we find for x bar?
The x bar is
Integral of wx dx. Yeah.
Divided
from
by r.
x0 to x1 divided by r. So this one is integral from 0 to 5. W here is what? 0.43 x to the power of 1.5 multiplied by x dx, right?
Yes.
Divided by r. R here is 9.62
yes
kilonewton. So now I will put it here. X bar is equal to integral from 0 to 5. Yeah. Okay, 0.45, 0.43 x to the power of 2.5, right?
Yes.
Yeah, dx. So what's the results there? I just put it like this. Okay, 9.62 multiplied by 1/3.5, right?
Yes, x to the power 3.5.
Okay, and the limit is from 0 to 5. Okay.
34.34.
Huh? 34?
34 point.
This one, this value, you mean?
Yeah, this, yeah. No, the total.
The total? Are you sure about that?
No, yeah. I'm sorry, sir. The total is 3.5.
Yeah, That's logical. 3.57 meters. 34 is not logical because the value is supposed to be between 0 to 5, right?
Oh, yeah. Yeah.
3.57 meters. Okay. So this is it. So our R value here is equal to 9.62 kilonewton. Our X bar here is equal to 3.57 meters. Okay.
Yes.
Then can we solve for this?
Yes.
You can, right?
I think.
Right?
Yes.
Using sigma fx equal to 0, then ax will be 0, right?
Yes.
And then using sigma fy equal to 0, what we have is ay equal to 9.62 kilonewton.
Yes.
Okay. And then using sigma moment at point A equal to 0. Okay. Sigma moment at point A equal to 0. What you have there will be MA is equal to minus 9.62 multiplied by 3.57 meters. So actually you get everything there.
Yes.
Okay. Seems like you understand.
Yes, I think so.
Okay, so later what we have is AY equal to 9.62 kilonewton, and then moment at A equal to, can you help me to find out that?
3.57. 34.34.
34.34 kilonewton meter, and the
Yes.
and it's supposed to be counterclockwise, right? Because the opposites of the current one, because it's minus, right?
Yes.
So this is the results. That's the way to do it. Okay. So actually that's all for all the things that you're supposed to understand related to the distributed force. Okay. Remember, before tomorrow's class, please try to watch the video, the second video that I post today about how to find the internal force at one particular point. Internal force at one particular point. Okay, I think that's all. That's all for today. Thank you very much for listening. See you guys tomorrow morning. Okay, please wake up early and meet you again tomorrow morning. Okay, see you guys.
Terima kasih banyak Pak Satrio.
Thank you very much, sir.
Thank you, Pak.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Bye bye.
Thank you, sir.